market model. This is the most popular model for interest rate in industry. So let's take a look at the intuition of the LIBOR market model. At the heart of the LIBOR market model is the specification of the dynamics for LIBOR-based forward rate under a specific dynamics. Specifically, consider a forward contract with maturity T and payoff. So it is forward contract for interest rate forward contract. So it's at maturity T, so payoff is N, which is notional amount, delta is time, and then Rn is interest rate at that time, at the maturity. No, not at the maturity. Yeah, last reset day. So this is the interest rate at the maturity. Basically, if it is end of October, then it is interest rate of the October, which is set at the beginning of October, something like that. Yeah. So it is the last reset day, the most recent contract interest rate, and K is the delivery rate. Okay. So this is your payoff. And then recall also that R and tau T denotes N times compounded LIBOR. So let's assume that it is N times compounded per year. In fixed income, usually N is 2 for every 6 months, which means that this delta is 0.5 time per period, 6 months. So the forward risk neutral pricing formula, as you remember, with numerator PRT, less PRT VTT implies that the value of this forward contract at time t is 0 becomes this one. Right? That's what we learned last week. Last Friday. Where the expected take on with respect to dynamic induced by the new numerator 0t, also called T forward risk neutral dynamics. So previously we put this one inside, but now by changing the measure we can put it outside. So the forward rate today, if we think about this contract as of today, it should be fair, so therefore the value of the contract should be 0, which means that this is 0. The forward rate today is the delivery rate K that makes the value of this contract equal to 0 today. So it means that in forward risk neutral dynamics, the expectation should be 0. Therefore, this implies that actually forward rate is expected spot rate. Not in objective measure, but forward risk neutral pricing. So in reality, interest rate, future interest rate, forward risk is a contract on future interest rate, but forward rate is not expected value of future spot rate. They are different because of risk premium. But if we take expectation in terms of forward risk neutral measure, they are the same. I think we learned this last week. In addition, forward rate must converge to spot rate at the maturity. Therefore, Fn tau tau t equal Rn tau t. So Fn 0 tau t means that at time 0 today, okay, 0 is today. At time 0, you make a contract. Okay, you make contract on interest rate between tau and tau t, tau plus 1 basically. Tau plus 1. So at time 0, you set interest rate for tau at the time of tau. But now you are tau. At time of tau, you set interest rate at tau, so it is basically spot rate. So at the maturity, they should be same. It is like the same that forward rate is the same, forward price is same to spot price at maturity. It's general result. So the LIBOR market model assumes that forward rate follows log normal diffusion price on the T forward risk neutral dynamic. And since this one is martingale, right? This one is martingale as we learned because expectation is same, right? So this is expectation at time t. So basically tau at time t, it is expectation of this one at time t. So it is kind of Dup's process we learn. So this is martingale, and it is martingale plus log normal process. Then we can, when the diffusion process for this fourth rate follows this one. And because of the convergence property of the fourth rate, according to which at time tau, this one, again they are same to this one, it follows under T fourth risk neutral dynamics, basically. So future interest rate, so this is interest rate, future interest rate follows log normal distribution such that mean is fn 0 tau t and variance this one. This is straightforward from this one. Okay, but it is not in reality. It is distribution under T4 risk neutral dynamics. So once we set the model like this way, it is very become convenient. So the live market model and the forward risk neutral dynamics method recover the black formula from no arbitrary. So from the forward risk neutral pricing formula, so PRT, VTT, the value of capital maturing at tau at Ti plus 1 looks like this one. So this is the final payoff. So capital is the, did I explain what is capital? So it is kind of option, capital. So there is a concept called the cap, and cap is a series of capitals, and capitals is like a call option on interest rate. So you have right to receive interest rate by paying RK. So RK, exercise price, exercise interest rate is RK. So it is like a call option on interest rate. So if interest, so once you observe interest rate, and then you have right to receive that rate and pay RK. Okay, so it means that if interest rate is greater than RK, which is exercise rate you said before, if interest rate is greater than RK, then you will exercise the right. You will receive higher rate and pay RK. Basically, you receive the spread between the two. If interest rate is lower than RK, of course, you are not exercising the right. So basically, caplet or cap is a series of caplet. Cap is used to protect you from high interest rate. If you are a fixed income manager, bond portfolio manager, and if interest rate goes up, you don't like it, then what you can do is you make a cap contract or caplet contract, such that if interest rate go up, you receive money rather than RK. In that way, you can protect your portfolio. Your portfolio lose money if interest rate go up, but given the caplet contract, you receive money if interest rate go up, so you can protect yourself. And it is a very, very popular contract. Very, very liquid contract. Liquid and popular contract. People trade this a lot. Anyway, so using forward risk neutral dynamics, we know the value of capital, whatever, is we put the expected value of the terminal payoff and we discount it, then we know this should be the value of the contract. So the value of a capital contract looks like this, and then this one is straightforward, but we have to compute this part. We know compute this part, but we know this one follows log normal distribution. So previous section showed that under this dynamic, the LIBOR, RN, the equation from this line, to this line, I made jump. The process is exactly same to the method we derived the Black-Scholes formula doing integration, right? Do you remember? We did integration and derived the Black-Scholes formula. The process is exactly same. We just put this one over here, an expectation, and then we have this one. This is the equivalent to, this is the basic Black-Scholes formula. Exactly same. Except to what we did. So this live market model is very convenient. We can price the Kaplan, one of the most liquid and popular contracts, and we can price with analytic formula. So this is very powerful and convenient. Very convenient. So why is it important to provide know of the framework for black formula? The answer is the usual. We can use quotes from the fact caps and floors, which is a relative liquid instrument, caps and floor. So cap is like series of caplet. Caplet is the call option, and floors. Floor is the interest put option on the interest rate. Floor is a series of floor rates. Okay, floor rates. And floor rate is actually put option on interest rate. Flip side of the Kaplan. And then those caps and floors are liquid. People trade this one a lot. Then we can calculate the model for forward rate and obtain the price of additional securities. Okay? So it is like we did in implied volatility. So this is the formula for Kaplan. But in the market, Kaplan is highly traded and very liquid. So market, we can guess the market price of Kaplan is likely to be correct. So once we have a market price of Kaplan, then we can recover the parameters within this equation. In this equation, everything is known. We know everything. This is what we can observe. Our case contracted rate. But this sigma f is something we have to estimate, either historical price or whatever. But once we know Kaplan, and since this term is a function of this sigma, we can recover sigmas. Okay, sigma f. Implied volatility. For example, the 1 year Kaplan has a forward volatility of this one. Yes, so previously we obtained the Kaplan formula volatility, that is the value of the volatility that would price correctly the Kaplan implicit cap quote. So for example, 1 year Kaplan has maybe some price, and if we use that price, and we can use this formula to recover this one, this is sigma f, then this is 25.54%. How can we use this information together with the current terms of interest to price additional securities? Okay, so once we now, from the current Kaplan price, okay, now we recover the forward volatility. Once we have forward volatility, now we can estimate any derivative written on interest rate. That's the power, right? Now we know this one. So we know future interest rate follows log normal distribution. This one, and this is something we can observe right now. Right now, people make forward contract in this way. And about this forward volatility, this is something we have to estimate. But now we know what is this one, which we recovered from the Kaplan price. So we know this one. Therefore, since we know the distribution of future interest rate, we can calculate any derivative written on future interest rate. Right? So, for example, consider a fixed income security whose payoff at time t equal 1 depends on LIBOR, something like this. So tau is 0.5. Then GT, the final payoff is GT in general rate. So it is derivative written on interest, future interest rate. So payoff is a function of some interest rate. If it is a call option, Kaplan, it is max R and minus RK0, something like that. So anyway, any general function of interest rate or some function, then what we can do is we simulate this one, calculate g function in each simulation, and we can get average it, and we are done. That's the basic idea. Okay. Because basically we now know the process of this one. We know the distribution, so we can simulate this one. So we are done. So what you can do is you can go back to this formula. So this is discount factor or zero coupon bond price, and you have to calculate this one. And for general function, we cannot get analytic solution. So we know this one Rn, the LIBOR market model assumes that under T forward risk neutral dynamics, forward rate follows log normal process, and we know this one is 25.54%. The same price is exactly a capital with maturity, because we will recover this one. We computed this one from the calculate. Therefore, the calculate for the volatility extracted from cash allows to fully characterize the process of the forward rate. Okay, so we use this one. Okay, so basically they are same. We know this one, and then it is log normal distribution. If we take log each side, then it becomes normal distribution, except some complexity adjustment. This one. So basically, this one is same to this one mathematically. Transform one to the other. And then if the function g were complicated, then we can do the Monte Carlo simulation. We simulate in future interest rate from this distribution and calculate this g function. And then we do it a lot and take average it and discount it, and we are done. This is something you did already in your homework. Thus, this is a basic idea of LIBOR market model. Any question? 질문 있나? 박남규 질문 있나? 무슨 말인지 알겠네. 잘 모르겠지. 좀 물어봐. 김대희는 이 결석을 많이 해서 아마 무슨 말인지 하나도 모를 것 같아. 지난 시간에 내가 설명한 데서 다 이렇게 돼 있는 거예요, 사실. 포워드 리스크 뉴트럴 프라이싱만 기억하면 돼요. 주변에서 무슨 말인지 알겠네. 무슨 말인지 잘 모르겠어. Bill, do you know what I'm saying? Can you guess what is going on here? Yes. Yes, kind of. So once we use a forward volatility, then we know the distribution of future interest rate. Like this one. Once you know distribution of future interest rate, then what we can do is we simulate future interest rate from this one, like 1,000,000 times. And for each 1,000,000 times, we calculate this G. Because for each simulation, we can calculate G, right? And we have 1,000,000 G values. And we average it. Then we have this term. And then we discount it. Then we have value. So easy, right? It's very powerful. Okay, good. So I mean, the key idea of this whole process, is this one. This one. Okay. So whole key idea is this one, calculate or where is it? key idea this one. Okay. First one. So we use numeral, and then once we, so instead of just the dollar, we use other asset as a numeral, and then we think about the ratio of the one asset with the other numeral as a new asset price, right? And then if there is no arbitrage, if we take into account the risk, once we get rid of risk, the ratio of those two asset price should not either converge or diverge. So it should be like stable, right? In the risk neutral world. Right? Of course, in reality, ratio of the Samsung Electronics and LG Electronics stock price can diverge in reality, in experience. It happens a lot because the risk of the two companies are different. But once we go into the risk neutral world, because people don't care risk, therefore the ratio of the two asset values should not diverge. That's a key idea. So we are thinking about that kind of a world. Okay? In that kind of world, the convenience thing is that now this V tilde is also numeral, which means that V multiply P is more numeral, so basically value of V looks like this one. So this is key idea. This is convenient part. So we apply this one. We apply this one into this one. We apply this one into one. Okay. This one. So basically, n delta t is constant. So we divide each side. So we use this z as a numeral. So if you divide this one with z t0, which it is basically this one looks like. Okay, we have this one. This one is basically, so they are the constant. They are the constant, so you ignore this one. So, right? This is the three. Right? What it says that this one is star, and this is a final payoff. Final payoff. T minus K. And divided by the TT. But the TT is 1, right? So this is we are using this zero coupon method as a numeral, right? So therefore V is this one multiplied with this one, right? So we have this formula. And then what we know is that this forward value of this forward contract should be 0 at time 0. Because it should be fair to each side. Then we can calculate K. Right? We can calculate K, which is basically it should be 0. We know it should be 0 because it should be fair. We can take each side. Then we know K should be exactly this part. So this should be so where K is the forward rate. Therefore, forward rate 0 tau T should be exactly the same to this one. Expectation of this one. Right. Therefore, we have a forward rate. And then we make additional assumption. We make additional assumption that, well now, this is we have this one. We know this one. But this holds for every time. So in general, we have F and T tau. T is basically E star F R and tau T at time T, at the information given T, right? And then we know this is martingale. learn this is martingale because we have something fixed and we are just updating information, right? And this is called the Dupes process, kind of, and we know this is martingale. And this is martingale, which means that there is no drift term. And in addition, we are assuming log normal process. We have this one. In this one, we have no drift term, and it is martingale. Special case of martingale. But we know it is martingale because it is drift term. Once we assume Fn now follows this one, so from this one, from the previous equation, we know this is martingale. It should hold, which implies that Fn is martingale, and we make additional assumption like this one, since it is martingale to 0. Once we make this assumption, then interest rate follows this convenient log normal distribution. Then using this one, so this Fn 0 tau t is something we know right now. The only missing thing is sigma f. If we can know sigma f, then we can simulate the Rn, future interest rate. Once we can simulate the future Rn, we can simulate any derivative price, that's maturity, and we can get expectation, we can discount it, we can get the current price. And then question is how we can get sigma f. This is easy. We use a Kepler. So Kepler price is given this convenient form, and then in the market we know Kepler price. So from market price we solve this one and we recover this one and plug this one into this equation, and we can simulate R and get the derivative price. That's the basic idea. 무슨 말인지 알겠나? 이제 무슨 말인지 알겠나? 조금 알 것 같아. 아, 이거 진짜 중요한 건데. 네? 정계 뭐. 그건 지난 시간에 안 왔으니까 그렇지, 당연히. 그러니까 지난 시간에 포워드 리스크 뉴트럴 매저를 안 배워서 그런 거지. 근데 포워드 리스크 뉴트럴 매저는 리스크 뉴트럴 매저 배웠잖아. 그렇지? 그거하고 거의 비슷한 거야. 리스크 뉴트럴 월드인데 이제 화폐 단위가 다른 세계지. 이제 리스크 뉴트럴인데 그 세계에서는 게다가 화폐 단위가 지로 쿠폰 본드지. 만기가 T인 지로 쿠폰 본드를 사용하는 리스크 뉴트럴 월드에 가서 이렇게 하는 거예요. 그런 차이만 있는 거예요. 그 리스크 뉴트럴 월드는 드리프트 텀이 지로겠지. 다시 말하지만. 왜냐면 에셋 프라이스 뭐 사람들이 그렇게 신경 안 쓰니까 에셋 간에 막 이렇게 컨버전 좀 스테이블해야지 관계가. 안 그러면 아비트리지 거래가 생기겠지. 사람들이 하나만 사고 하나 팔고. 영업의 핵심은 그거예요. 위에 리스크 뉴트럴 프라이스. 이거 굉장히 중요한 겁니다. 이거. 나중에 여러 금융권에 취직해서 인출했을 때하고 라이브 마켓 모델 누가 막 그러면 기억이 나야지. 물론 여의도에서는 라이브 마켓 모델을 잘 안 쓰고 펄 화이트 모델이라고 여러분하고 같이 푼 거 그걸도 많이 쓴다지만 외국계 IB도 상대할 일이 있을 거 아니야. 외국계 IB에서는 다 인출해서 라이브 마켓 모델 쓰는데 뭔지는 알고 있어야지. 그래서 그냥 라이브 마켓 모델이 이거구나. 물론 이것보다 살짝 더 복잡하고 제가 좀 더 설명하고 기본적인 아이디는 이거랑 똑같아요. 아무튼 이제 이자율 파생, 여러분 이 세상에 존재하는 모든 이자율 파생상품 이제 계산할 수 있는 거야. 이걸 이용하면 이자율 시뮬레이션에서 파생상품 터미널 프라이스 구하고 디스카운트만 하면 되니까 에버리지 그래서 R도 이제 여러분 할 수 있고 R도 할 수 있고 모델도 알고 그러니까 진짜 뭐든지 다 계산할 수 있는 거지. R로 캐플리 프라이스 풀어가지고 시뮬레이션 해서 그래서 저 이자율 디펜던트 파생상품 이렇게 계산. 어느 한 기의 이자율. 네. 이제 문제는 그 다음 단계면 이제 어느 한 기. 여기서는 이제 어느 한 기. R 타우 T. 타우 시점에서 모은 스팟 레이트. 스팟 레이트에 디펜던트한 이제 파생상품은 뭐든지 구할 수 있는데 이제 문제는 근데 이제 언더라잉에서 채권이다. 그러면 채권은 그 딱 시기만이라 중간 단계 인트레스트도 다 필요하지. So now you know how to get the price, how the price of the derivative depends on single spot rate at time tau. Now you can calculate any derivative price, but some derivatives depends on series of spot rate. Right? For example, bond price. Bond price is function of series of spot rate at time t minus 1, t minus 2 up to the 0. Price of zero coupon bond depends on structure of interest from today to the future. In that case, it depends on many spot rate. In that case, you have to use a slightly more complicated model, which is I will explain shortly. But at least if you derivative between the single spot rate at some point, then you can do it. Although you cannot calculate like derivative written on bond, which depends on series of spot rate, which is different matter. But this is derivative price just single spot rate. Now it is doable. It is easy. So there is even example. Okay. Let's take a look at the example. My original plan is to skip this one. But let's take a look at the example. This is a very strange, somewhat strange derivative. At the mature, so it's a square of the 3-month LIBOR. So it is like similar to call option. It is similar to cap rate. If there is no square term, it is cap rate. But now you square. You square, and then this is notional amount. So this is the final payoff. Then how to calculate it? Because it depends on single spot rate, we can simply use the formula or method we just learned. Let's assume that this N is $100 million, and then tau is what? 9 months. What? 9 months. T is 1 year. Okay. So it is spot rate from 9 months later to 1 year later. So 3 months rate, 9 months later. Okay. So what you receive is 9 months later. Okay. Actually 1 year later. 1 year later, your payoff will look like this. Depends on interest rate at that particular quarter, last quarter of the year. This is called power option because we have powered it. Let the current forward rate is this one. Now we know current forward rate, and from the capital price, maybe capital price, and if we solve out this one from capital price, and then we can recover this one, and suppose from the process we get the forward volatility is this one, 25% or 26%. Then we can calculate this one. Right? Yeah. So one idea is that idea one, method one is now we know the distribution of this Rn. So since we know current for the price, current volatility, we can simulate this one. For each simulation, we calculate GT and get average discounted back. This is what you learned, right? This is very easy. That's the method one, which you can always do. But this particular power option, actually analytic solution exists. Right? Because the idea is like this. Because Rn follows log normal distribution, so it is exponential function of some normal distribution, and it is square. So it itself is follows the normal distribution. Since this Rn square follows log normal distribution too, we can get analytic solution, right? So Rn form of E of epsilon, something like that. Epsilon is normal distribution, and the square, so it is E to the power of 2 epsilon. So it is still log normal distribution. So we can get analytic solution. Of course, you can, again, method one, you can do the simulation. Method two, this one, by noting that Rn square follows log normal You can actually solve this one by pencil and pen. No, pencil and paper. Okay. So let's take a look at it. How to do that one. A convenient property of power option stems from the property of log normal distribution. Because if you square log normal distribution, the square is again log normal distribution. In particular, if a variable x is logarithm distribution, x, ex, and variance like this one, then for any constant alpha, x alpha also normal log normal distribution with this one. We know this from this one. You can prove this one easily by integration. It follows that we can obtain an analytic formula for power option with any alpha because you know variance and it follows log normal distribution. So basically denotes the T for the distribution is 3 months live raised to the power of alpha power and then its variance respectively. Then this one, it follows this one and this one. It is simply application of this one. This is same to this one. Instead of x bar, we just put the fourth range because expectation alpha is fourth range. And instead of build velocity, we just plug fourth velocity. So this one, we have this one. Right? So the power core option is we can simply plug the previous formula. We can also drive it. So the analytic solution looks like this and D1, D2, sigma T and this one. Again, this is Z this term and sigma T this term is basically zero. So power core when alpha is 2 is this one. When alpha is 1/2 is 1.5. Another example. Now, so this is another example. Now, the terminal pair looks like this. GT is nominal exponential of tau, and we have some absolute value. K is strike price, and lambda is some sort of parameter. We have this one. Figure 21.1 plus the pair for lambda is 300, K is 0.56, and is $1 million. And no wonder it looks like this. So this particular contract, if LIBOR is this one, you make most of money. But once the LIBOR rate diverges from the particular rate, you quickly lose money. So basically, it is kind of contract so that you bet this particular point. Since we know that on the T for the distributional dynamics, the 3 months LIBOR has a log normal distributed F and this one. Okay. We are iterating this one. So process is simple. Okay. From the log normal distributor, we obtain simulated value of Rn. We do the simulation. We can do this by this one. So this one is simply from this one. Rn follows log normal. So if we put expectation each side, no, exponential each side, then Rn is something like this. So this is this. So from this one, we have this one. So this expectation minus half of this one, and then the rest of it. So standard normal distribution. So we simulate this one, and then for each simulation we calculate this one. And then we come to the value of security as the average. And we are done. We have the answer. The way to simulate it is obvious from this one. You can simply compare this one and this one. And this one you can compare this one and this one. Okay, the only difference term is this one. Convexity of this one. It is always there. And I explained it by comparing mean of the return and average return. I think I explained why it is there previously. I don't know why it's there. Because average return is different from mean of the return. we are done. Now, more complex. Let's calculate more complicated one. Now we want to calculate derivative price, which is slightly more complex. Basically, it depends on not single spot rate. In the previous case, the derivative depends on single spot rate. But now we have a series of. Now we have a derivative depends on underlying asset, and underlying asset, the value of underlying asset depends on series of spot rate. How we can do that? Let's formulate the problem first. More work needed, however, to price other security that depends on many forward rate. In for the case in which forward rate depends on single factor and is perfectly correlated. For example, consider relatively simple security that at time T bar has a payoff depends on 3-year zero coupon bond. Okay, so it is the derivative. This particular one is derivative written on bond, future bond price. Okay, so at time T bar, which is future. Now at that time in the future, we will have a bond maturing 3 years later at the time. And our derivative depends on that bond price, zero coupon bond price. Then how we can do that? Of course, the idea is similar. We want to simulate bond price and get the average and discounted. That's our idea. The problem in evaluating such a security that in the live market model, we are modeling forward rate dynamics and not zero coupon bond, right? We are modeling rate, not bond price. In the other letter, try to apply the same logic used to price securities that depend on one individual live only as in the previous section. So what would we want? In ideal situation, what we want is that, okay, this is something we want, okay. T bar for the risk neutral dynamics, we want to formulate the value of this contract in this way. Okay? This is something we want. Okay? So if we can write this way, we can simulate this one. We can simulate the bond price, and then by simulating bond price, we can simulate the G and average discounted, and we will get that. This is what we want, basically. This is our goal. The second step to use the statistical distribution Z under T for the risk to compute the expected. But this is plus. So what is the statistical distribution of Z T bar plus 3? In order to do this one, we have to simulate this one, Z T bar plus 3. But we don't know the statistical distribution of this one because it depends on many forward rate. Many spot rate, many insurance rate. So what is the statistical distribution Z? If we know statistical distribution Z, we can simulate it, but it turns out that this is not obvious. From the first principle, we can map bond price into the forward rate. In fact, assuming that N is a compounding frequency, suppose N is a compounding frequency, usual bond N is 2. For every 6 months, we receive cash, which means that delta, which is the time period, is 6 months, usually. But anyway, let's make it general. So N is compounding frequency, and delta is 1 over N. And red I bar is the step index corresponding to T bar, that is T bar equal to T I bar. Okay, so in this case, T bar plus 3 is T I bar plus M. Then zero coupon bond price is generally written in this way, right? At the terminal day, we receive $1 and we discount it. So zero coupon bond price written in this way. Now from the joint statistical distribution of forward rate, so now we have a bunch of forward rate and we have a future interest rate. Right? So idea is how we can then from this one, we have to simulate each one of these one. How we can simulate each one of this one. Okay. If we can simulate each of these forward rate and the future interest rate, this is something we can, but others are not. If we can simulate each one, then if by simulating each forward rate, then it means that we can simulate Z. Then the question is how we can simulate each forward rate. That's the question. 질문이나. 이건 내가 특별히 설명 안 해도 이건 이미 아는 거잖아요, 여러분. 롱텀 레이든 숏텀 레이트, 숏텀 레이트에다가 포워드 레이트를 쭉 이으면 되는 거. 이건 여러분이 알 거고. 그치? 이건 여러분이 알 거고. 그거 배웠잖아. 2년간 장기 스팟 레이트, 1년 스팟 레이트에다가 1년부터 2년 사이 포워드 레이트 곱한 거랑 똑같아야 되잖아. 아무튼 그 말이에요. 별거 아닙니다. 이걸 본드 프라이스로 풀어내면 이건 여러분 알고. 그러면 이 하나하나들을 시뮬레이션 해야 되는데 딱 하나만 찍으면 우리가 할 수 있어. 지난 시간에 이제까지 한 것처럼. 근데 이건 지금 여러 개의 디펜던트 한 거란 말이야. 이거 어떻게 하냐는 거죠. 이렇게 여러 개의 디펜던트 한 건데 이 하나하나라도 시뮬레이션 하는 거다. 네. The problem is that the live market model assumes that each forward rate is log normally distributed on the TI forward risk neutral time as induced by normalization. That is, each forward rate follows the process. But each process is defined in terms of a different numerator. Right? We have a different numerator, TI, namely CTTI plus for forward rate maturing at time TI plus 1. So numerator is different. So we have to make it same. Recall that this assumption is required for live market model to price exactly the capital cost in the market through black formula. The reason why we also allow for different volatility across forward rate. Right? In general, this is that this can depend on time. Okay, for each maturity, this can change function of time. So in general, or without. For the general relative, we express as function of t. Anyway, the problem is that the dynamics of the forward rate under the common t forward dynamics need to evaluate the pricing is not log normal. That is a problem. If we use different, so our numerator, our goal is, because of this one, we want numerator this one. First, we set numerator this one. Then each forward rate doesn't follow log normal distribution. Each forward rate follow log normal distribution with their own numerator. But once we use different numerator, they don't follow log normal distribution. Then we cannot simulate this one. That's the problem. Then how we can do that? Fortunately, we have this formula. Looks complicated, but we have this formula. We can derive this formula, but you don't have to at this point. So the dynamics of the forward rate under the T bar forward risk neutral dynamics for T bar is less than Ti is given by this one. This is formula. Okay. Once you can derive it, but it is complicated, so you can just remember. It looks like something like this. If instead T bar is greater than Ti, looks like this. So it means that now if we use different numerator, we have drift term, complicated drift term. Right? This term is the same, but we have a complicated drift term. That's the only difference. So if we use common for the risk neutral measure, then we have something like this. It looks complicated, but still we can calculate it. So anyway, once you look at this one, the only thing you need is basically this one, sigma thing. Sigma thing. Other thing is something you know already. Other thing is this F thing is you have to simulate. So they are all dependent on sigma volatility. Right? So once you know this sigma, you can simulate all forward rate using this one. The key input in forward rate dynamics is the following strategy. This one, considering sigma I plus 1 constant. Okay, so in order to take a look at the big picture, okay, the question is this one, this forward rate volatility. Suppose we know this one. Then we can calculate derivative price. Okay, let me jump further. Suppose we know these sigmas. Then we can jump, and then what we can do is we can do Monte Carlo simulation and calculate any fixed income security now, given the volatility specification obtained in the previous section. Okay, I will explain this one again. We can use the forward dynamic to price a security with maturity T bar. Okay. We can perform this rest with Monte Carlo simulation. We can discretize the process with time step delta, simulate random normal shock, and multiply by delta 1/2 and use them in lieu of Brownian motion dxt. Okay, it is convenient to simulate the logarithm of fn. That is, we use the scheme. Okay, so we simulate t plus delta thing. Okay, Okay, this one from this one. Once we suppose we simulated this one, then we can simulate this one. Okay, so m here, it is a previous formula. M looks like this, and we have a convexity adjusted sum. So once we have f and t thing, we can simulate the other one. If we simulate the other, we can simulate the next step by step. Note that we have to simulate all the forward rate at the same time as the forward rate enters the process of fn, sti, and vice versa. Note that same simulation shock affects all other forward rate, because we are just assuming we have just one shock like this one. So from time t, we can simulate future forward rate. So this example today, November 1, 2004, and the speculator wants to purchase a 1-year call option on 3-year LIBOR discount factor where T0 is 1 and T0 is 4. Okay, so it is 3-year LIBOR discount factor. The payoff looks like this one, and then under T0, which is T0 is the 1 year, then the value looks like this one. So we have to basically simulate this z term. Okay, the value of the option crucially depends on volatility with z. We can use the cap price to infer the market expected volatility. This one, which I will explain later. In fact, as discussed earlier, denoting I is quarterly index for which T naught is this one, and I bar plus M is this one. So we are discretizing. Then we proceed as follows. Use cap prices to say to collaborate the volatility. Basic idea is like this one. This is done in the previous example under the assumption that this one is an I'll explain this again. And suppose we estimated all volatilities from cap prices and express the dynamics of the forward rate on the T0 dynamics. This one. We can simulate this one. And then simulate the forward rate. Once we simulate forward rate, we can easily compute the ladder as from the forward rate to determine the discount curve, this one, for any mature team. Note that the short term of the simulated forward curve corresponds to 3 months LIBOR, implicit simulated here as well. And repeating this simulation after 10,000 times. And then we simulate this one and calculate the value and discounting and average it, and we have the derivative price, this bond derivative price. And it is another one. It is a European receiver swaption. Swaption is an option to enter swap. And then so you can check the book what is swap, but anyway, the payoff of swap looks like this. Again, it depends on the future bond prices. Again, the same. We can simulate this swaption payoff like 10,000 times, average it, and we can calculate the value of this particular swaption. Another example is all same. So the idea is basically the same. Okay. The idea is basically we using this formula, we simulate all forward rate, and then series of forward rate. And if we see a series of forward rate, we can have a more complex security that depends on series of forward rate or interest rate. And then we can simulate it, and we can get the average it and discount it back, and we can get the price of the price. So the question is now how we can calculate this forward rate volatility. I think calculating forward volatility is a big topic. And then this is quite technical and uninteresting. There's no economic intuition about that. So I recommend you to read, study yourself. 그러니까 여기서 이제 forward rate volatility를 어떻게 계산하느냐. forward rate volatility 하나는 어떻게 계산하는 방법이 되게 디테일하게 나왔어요. 디테일하게 나왔는데 별로 거기에는 이코노믹 인투이션 없고 그냥 테크니컬한 거라 그냥 전에 책 보고 읽으면 돼. 별로 어려운 거 없어요. 그건 여러분이 갖는 거예요. 어쨌든 아이디어는 뭐냐면 캐플리 프라이스에서 가져온다는 거. 그리고 하나의 방법만 있는 것도 아니고 캐플리 프라이스에서 뭔가 추정해서 여기에 끼워 넣으면 되는 거지.
아마 여러분이 오늘 배운 건 굉장히 파워풀한 거고 인더스트리 스탠다드라고 하시는데 좀 어려울 수도 있어요. 어차피 학부에서는 잘 안 배우는 건데 학부에서 이걸 가르쳐주는 사람은 나밖에 없을 것 같아요. 네. 일단 나는 그렇게 생각하거든요. 어렵고 이해가 안 되더라도 한번 들어본 것과 안 들어본 건 차이가 있다고 생각해요. 여러분 인더스트리에 가서 이제 라이브 마켓 모델하고 공부할 필요가 있을 때 한 번 배운 거면 어디 책의 어느 부분을 찾아서 어디를 공부하면 되는지 이제 알잖아. 최소한 그게 중요한 거지. 게다가 한 번 설명을 들었으니까 오늘 복습하고 그러면 오늘 이해를 해놓으면 잊어버려도 나중에 그런 거 배웠다는 거만 기억하면 책 찾아서 다시 읽으면 그때 더 잘 이해가 갈 거거든. 그게 중요한 거지. 지금만 이해하고 힘들어. 어쨌든 제 생각에는 뭐 특별히 이해하기가 그렇게 어려운 건 아니라고 생각이 되기 때문에 내가 차근차근 설명해 줬기 때문에 집에 네? 책이 있지. 내가 책 소개 안 했나? 이게 책이 어디서 나온 거냐? 물론 이 PPT만 봐도 돼요. 근데 PPT만 보면 설명이 부족하고 좀 더 잘 이해하고 싶을 수 있잖아. 네, 그러니까 이 부분은 굉장히 중요한 건데. 네. 책은 우리 보면 내가 소개를 했는데 여기 있네. 텍스트북 이거고 특히 이겁니다. 이걸로 집중적으로 설명한 겁니다. 피에트로 베로네즈 아이라는 시카고 대학 교수님이 쓴 책이 있어요. 네. 제 채권 수업 교재로 쓰는데 어쨌든 이 책의 챕터 21을 보면 물론 처음부터 안 보고 어떻게 갑자기 챕터 21을 보냐 읽을 수 있어요. 제가 차근차근 여러분 혼자 공부할 수 있을 만큼 지금 설명을 해줬기 때문에 챕터 21 보고 공부합니다. 아무튼 여러분이 이제 시장에 나가서 마켓에 나가서 이자율에 관해서 이제 적어도 이자율에 대해서 필요한 건 다 배운 거야 여러분이. 네. 이자율 파생성 채권 수업은 여러분이 또 들었을 테니까 박동규 교수님에 대해 수업 들어오고 하니까 어쨌든 이자율 파생성분 시장에서 이제 주식에 대한 것도 여러분 뭐든지 다 배웠고 채권에 대한 것도 배웠고 아무튼 시장에서 존재하는 웬만한 파생 상품이나 이런 거에 대해서는 이제 메커니즘을 여러분은 다 배운 거예요. 다 배운 거고 이 정도만 있으면 이 이상 하지도 않아. 인더스트리에서 내가 지금까지 가르친 거 이 이상 하지도 않습니다. 별로. 이거면 진짜 충분해. 이거면 전 세계 어느 증권회사에 가서